Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. Okay, well, let's just jump right into the first listener phone call.
Hello, my name is Cliff from Cupertino, California. My question relates to reactionless propulsion. And when I say reactionless, I do not mean any false impressions like electromagnetic levitation, centrifugal force, or anti-gravity, etc. Today, if I tell anyone about a concept for reactionless propulsion, everyone suggests me to first develop a theory which would be hundreds of times harder than just conducting the experiment and finding it out. On the other hand, whenever we enabled frictionless motion, I mean invention of wheel, the actual theory was followed thousands of years later. Why is this contrast? Has the theoretical advancement become a barrier to non-incremental experimentation? Especially because current theories, which by the way are great for incremental stuff, but we do not know whether they will even turn out to be consistent with the reactionless propulsion or not. Your thoughts, please. Thank you.
Okay, well, first of all, I'll give you a reaction to your question about a reactionless propulsion, and then I'll give you some advice about what to do with your theory. First of all, we have Newton's 3 laws of motion, and reactionless propulsion would violate the third law. Let's go through the 3 laws very simply. The first law of motion, you know if you go ice skating, and that is an object in motion, stays in motion unless acted on by an outside force. So if I have an ice puck, for example, and I throw it on an ice rink, it seems to go on forever. In fact, it will go on forever if it wasn't for friction, which is an outside force. So in outer space, if you are in motion in outer space, in principle, you go forever without stopping. And that's how our space probes can go all the way out to Pluto and beyond. They coast. They coast once they're in outer space. They don't need rocket fuel. They don't need large amounts of gasoline to reach Pluto. No, they simply coast because there's no friction in outer space. The second law of Newton is force is equal to mass times acceleration. That gives us equations by which we can calculate the tensions on a bridge, the tensions in a rocket ship, and the tensions in the Empire State Building. You know, when I was a kid growing up in California, I used to hear about the Empire State Building, and I used to wonder, how can they build the Empire State Building without knowing ahead of time if it's going to fall down? I mean, you can't make a model, right, of the Empire State Building that's realistic. So how do they know it's not going to fall down? Well, the answer is we have Newton's second law of motion, and that allows you to calculate the stresses on every single brick inside the Empire State Building. In fact, now that I teach physics, I actually give students problems like that, calculate the tensions inside a bridge. Next, we have Newton's third law of motion, which deals with reaction. The third law of motion is known to every child who's ever blown up a balloon. When you release the air on the balloon goes shooting out in the opposite direction. So air goes in one way, out the nozzle, and the balloon goes the other direction. That is action-reaction. Now, what this listener proposes is a reactionless propulsion. That is, propulsion like a rocket ship without the rocket. That is, without the exhaust. Now, that'd be great. For example, if I have a reactionless propulsion for a gun, I can shoot the gun and not feel the recoil. But if you ever fired a gun, and I fired many guns because I was in the United States military for about 2 years, when I fired machine guns when I was in the military, I realized that there was a back reaction on my shoulder. And therefore, you have to sort of grit your teeth, knowing that when you fire a machine gun, you're going to get that rapid-fire reaction on your shoulder, which could actually hurt. Now, same thing with rockets. If you have a reactionless propulsion system, it means you can have the rocket without the fuel. In other words, it would take off pretty much all by itself, because you need the fuel for action, and then the reaction is motion in the forward direction. Well, so far we see no violation of Newton's third law of motion. We have skyscrapers, rockets, bulldozers, buildings. At no point do we see a violation of Newton's third law of motion. That's why some people think that the search for a reactionless propulsion is futile. Now, let's say you have a theory, then what are you going to do about it? Some people are hesitant to publish that theory because then your rivals will scoop you and steal your invention. Well, what you ought to do is several things. One, get a patent. In fact, you may want to consult with a patent attorney to get that patent. However, many patent officers require a model that works. Well, let me take a short commercial break, and after that break, I'll give you a word of advice if you have a great invention and you want to make sure that no one steals your idea. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Before the break, we had a question about reactionless propulsion. Many people have tried to create that because then you could basically have motion without the rocket fuel. Think about that. Rockets without rocket fuel. However, Newton's has the last word. For every action, there's a reaction. And we know that because we've tested it on rockets, airplanes, we've tested it on bulldozers, skyscrapers. Every time there's an action, there is a reaction. And that's codified in something called the conservation of momentum. So, sorry about that. If you are an inventor, I would suggest you try to invent something else other than something that violates Newton's third law of motion. However, if you do have a theory, what are the steps that you should pursue? Well, first of all, you may want to take a patent out on it. However, I warn you that if you have a patent for a perpetual motion machine, usually they ask for a demonstration model. So many people over the centuries have claimed to have created a perpetual motion machine. Energy from nothing. In fact, in antiquity, going back thousands of years, enterprising inventors would go to the king and claim that they can get energy for free. Usually it was some kind of spinning wheel of some sort. And of course, because of friction, you basically lose energy and have to add energy from the outside. But anyway, over thousands of years, people have tried to get inventions sponsored by the king, in which case they could become millionaires in the process. However, after centuries of analyzing all these perpetual motion machines, we physicists have come to the conclusion that there's something called the conservation of energy, which in turn is a byproduct of Newton's laws of motion. So in other words, the patent office will ask you for a demonstration model. Don't just think you can create something in the laboratory and become an instant millionaire. However, I do suggest that if you do have an idea, patent it. Talk to a patent attorney. Or if you simply want recognition for your idea and not necessarily to commercialize it, publish it in a magazine. There's several magazines you can submit it to. There's Physical Review, which is the magazine of my organization, the American Physical Society. It is the premier American physics magazine, Physical Review. There's also a European magazine, Nuclear Physics, for example, published by Elsevier Publishers in Europe. They are one of the leading publishers of nuclear information papers in the nuclear field. So if you have an idea and you don't want to patent it, but you want recognition for that theory, then you may want to send it to these magazines, and then you will get a referee. Sometimes more than one referee. In fact, I referee other people's papers all the time. Magazines send me articles to referee for their magazine. In fact, just last week, I got a article that a magazine wanted me to referee an article about astronautics of interstellar space travel. So those are the paths you can take if you have an idea and you don't want someone else to steal that idea. By the way, don't take it personally. Sometimes the referees can be brutal, but they'll be honest with you. The referee will tell you honestly why they think your idea is great or why it's a bunch of nonsense. Okay, let's move on now to the next listener phone call.
So you know how you can lucid dream? Oh, this is Armand again from Queen, listening on YouTube. So you know how you lucid dream? I was wondering, if there's one day you think there'll be technology to make you able to control your dreams while you're sleeping, so you can actually function on in a virtual world while you're sleeping, while you're getting like a good night deep sleep. All right, thank you very much for that, and I love your show, and have a great day. Bye.
Okay, good. Well, just a few years ago, if you were to ask a question to a scientist about lucid dreaming, they would have considered you to be a crackpot. Well, not anymore. Lucid dreaming, that is the idea that you can control the progress of a dream, is actually correct. There are lucid dreamers who've been subjected to an MRI scan. When they fall asleep inside an MRI machine that analyzes blood flow. It turns out that when you dream, the blood to the prefrontal cortex, which is the thinking part of your brain behind your forehead, shuts down. That's why your dreams become fantastic. They violate all the laws of logic, not just the laws of physics. They violate the laws of logic because the front part of your brain is drained of blood when you dream. And then MRI scans show that the center part of your brain, that is the amygdala, lights up like a Christmas tree. And that's the seat of nightmares, the seat of emotions, the amygdala. And that's one reason why many of your dreams are nightmarish. So it turns out that people who are lucid dreamers have an active prefrontal cortex while the amygdala lights up. Both areas of the brain light up. So in other words, it's true. Not only that, but when you dream, you are paralyzed. So how do you talk to someone who's a lucid dreamer? You give them a piece of electrode in their hand, and you ask them to squeeze it. Even though they are paralyzed when they dream, they have the ability to squeeze gently an electrode in their hand. And that's how you can communicate. That's how you can actually talk to someone who's dreaming and communicate with them. And they can communicate with you by squeezing this electrode. This has actually been done now at the Max Planck Institute in Leipzig, Germany. They put a German who claimed to be a lucid dreamer inside the machine, and bingo, the prefrontal cortex was fully lit up even as he was in REM dreaming state. So in other words, lucid dreaming is scientifically possible. Then the next question is, how do you become a lucid dreamer? It turns out that Buddhist texts going back centuries have given people lessons as to how to become a lucid dreamer so that you can control the direction of your dreams. You can Google it. Some of these things are common sense. One is that just before you go to bed, you have a notebook. You see, when you wake up right after a dream, you forget the dream within a matter of seconds. Within a matter of seconds, the memory of that dream simply disappears forever. So have a notebook. Write down the dream. Get in the habit of writing down the dream as soon as you have it, as soon as you wake up. Second, prime yourself. That is, before going to bed, say to yourself, I'm going to be a lucid dreamer tonight. I'm going to be awake. I'm going to control the direction of my dream. So get in that frame of mind that you are going to control the direction of your dream when you dream that night. Now, of course, we can't guarantee that you're going to become a lucid dreamer. However, the lessons are centuries old as to how to control the direction of your dreams. This is not science fiction anymore. We actually can do it now in the laboratory. Okay, let's move on to the next listener phone call.
Hi, Dr. Kaku. My name is Tim. I'm calling you from Dallas, Texas. My question regards dark matter. Is dark matter just matter that we cannot observe via visible light, or is it just something nebulous and unknown in the universe? I know that it makes up so much of the universe, and we don't know very much about it. So your thoughts on the matter would be very well appreciated. Thank you very much.
Okay, good question. Well, every high school textbook has to be rewritten. All the high school textbooks say that the universe is basically made out of atoms, but that's not true anymore. We know that there's something called dark matter, which outweighs ordinary matter by a factor of maybe up to 10. Now, how do we know that? Dark matter was first found by astronomers decades ago, but it was dismissed because it was too preposterous. For example, the Milky Way galaxy spins. It looks like a pinwheel, in fact, but it spins 10 times too fast. By rights, it should fly apart. In which case, the Earth should have been flung into outer space billions of years ago. But the Milky Way galaxy is quite stable, and we see these galaxies everywhere in the universe that are very stable, but all of them are spinning about 10 times too fast. Either this means that Newton was wrong, and we are very reluctant to give on Newton's laws of gravity. Either Newton was wrong, or there's a new form of matter in a halo surrounding the galaxy, keeping the galaxy intact, preventing it from flying apart. That's dark matter. Now we have maps of dark matter. Dark matter is invisible because when you photograph these galaxies, we don't see a halo around these galaxies at all. We just see a pinwheel. But they're stable, and they spin 10 times too fast, and we now have maps of dark matter. When light goes through glass, it bends light. So how do you know that there's glass inside your glasses? Well, glass is invisible. So how do you know that there's glass inside your glasses? Because light bends when it goes through your glass, and that's why you have eyeglasses. Same thing with dark matter. When light goes through this invisible matter, it bends. Then, using a computer, we can calculate how much dark matter there is by calculating how much bending of light there is. And you can Google it. You can actually see maps of dark matter reconstructed using computers looking at the bending of starlight. Well, let's take a short break, and afterwards we'll talk about what is dark matter anyway, and why should you care? To Science Fantastic with Professor Michio Kaku. Before the break, we had a question about something that is requiring us to rewrite all the high school textbooks, and that is the presence of dark matter. What is it, and why should we care? Well, first of all, as we mentioned before, we have maps of dark matter which surrounds the Milky Way galaxy, holding the galaxy together so that it doesn't fly apart. And the next question is, what is dark matter made of? Well, the short answer is we don't know. There's a Nobel Prize waiting for that person who can finally tell us what dark matter is. However, there are many theories. The leading theory is that it's a new particle. We call it the photino, a particle that is the companion to the photon, which is a particle of light. The photino is invisible. It is predicted by a theory called string theory, which is what I do for a living. And it is plentiful and invisible but has mass. These are exactly the characteristics you want dark matter to have. You want it to have gravity, so it holds the galaxy together. You want it to be invisible, because we don't see anything with our telescopes when we look for that halo surrounding the galaxy. And this particle is predicted by string theory. String theory has not been proven, but it simply says that all matter consists of vibrations. Vibrations of a tiny rubber band. When the rubber band vibrates in different frequencies, you get different subatomic particles. Now, why don't scientists all uniformly agree with string theory? It's a controversial theory. Among other things, it states that the universe is not three-dimensional at all. We think that everything is three-dimensional. You can describe everything by its length, width, and height. However, string theory says that there are 11 dimensions, that our universe is a bubble floating in a much larger hyperspace universe. That's controversial. That's why some people don't like string theory at all, because it forces you to confront a many worlds. The idea that our universe is not just one bubble that's expanding, an idea given to us by Einstein, but there could be many bubbles out there, a multiverse of universes. Now, there is another way to explain dark matter, and that is, if there are these other universes, then matter can exist, stars can exist in these other universes. If these two universes are close together, we would feel the effect of gravity from this other universe, but it would be invisible, because light can only move in our bubble. Therefore, if you hover in hyperspace, you are invisible, but you exert gravity. But that's exactly what dark matter is. It's invisible, but exerts gravity. Now, that is a pretty wild theory, a theory that we are very close to a parallel universe where there are parallel galaxies out there, and that's what causes the halo. Well, personally, I believe in the first theory, that is, for the photino, that is a particle of the photon, is the origin of dark matter. And why should we care? Well, first of all, we are here today because of dark matter. If it wasn't for dark matter, the galaxy would have been split apart, would have been flung apart billions of years ago. And if it does turn out that dark matter is consisted of these higher resonances of the string, it'll prove one of the greatest theories of all time, that string theory is in fact the theory of everything, the theory that explains the entire universe, the fabled unified field theory, the theory of everything. But that's another story. Okay, let's move on now to the next listener phone call.
Hello, sir. This is Bear, spelled B-A-I-R, Bear Cloth. I found your question on Twitter, and I'm from Medford, Massachusetts. And my science question is, in this universe, is a black hole the other side of the Big Bang in a different universe?
Well, at first your idea sounds ridiculous and preposterous, but actually there are physicists, colleagues of mine, who actually published papers in this idea. And this idea is very simple, and that is, if we have black holes, why can't we have white holes? In fact, Stephen Hawking wrote papers on this, the fact that somewhere in the universe there should be the opposite of a black hole, which is a white hole. A white hole, instead of absorbing matter, actually excretes matter, shoots matter out. And then the question is a white hole on the other side of a black hole? Well, we'll talk about that after the break. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a question about white holes. So let me explain. First of all, the laws of physics can run forward or backwards in time. For example, if I get a motion picture and I reverse the direction of time, then, well, bizarre things happen. Food comes out of your mouth and reforms to give you breakfast right in front of you. Dead people come out of graves and reassemble to become living people. So if you ran the videotape backwards, it would be very strange, but possible. Unlikely, highly unlikely that food will come out of your mouth and reform to create the fried egg that you had this morning, but possible. So if you have a black hole that absorbs matter like a vacuum cleaner, then a white hole should also be possible. Unlikely, but possible. But we've looked for white holes and we have not found any at all. But white holes are actually rather convenient because if everything falls into a black hole, then maybe it spews out the other end as a white hole in another universe. Now, this idea was actually made possible by Einstein himself. In 1935, he asked himself a simple question. If you fall into a black hole, does all matter basically die at that point? What happens to the matter? Maybe it funnels out into another universe. So think of a black hole as being a funnel. A funnel where everything comes in, nothing comes out. But on the other end of the funnel, there's a reverse funnel that's upside down, and it's attached to the original funnel. So you have two funnels. One funnel, which is the black hole, which absorbs everything, and the other funnel shoots out matter, and that's a white hole. And then several of my colleagues have said, maybe that's the Big Bang. Maybe the Big Bang is really connected to a parent universe. Now, as bizarre as this sounds, this is compatible with an idea called inflation. And inflation, in turn, is the leading theory of the Big Bang. It turns out that Alan Guth at MIT proposed the idea of inflation several decades ago. It fits the data. He may eventually win the Nobel Prize for this theory called inflation, which says that our universe can peel off baby universes. So think of a soap bubble, and the soap bubble can peel off baby soap bubbles, and you have this continual peeling off of baby universes. In other words, Big Bangs are happening all the time. Every time you have a peeling off of a baby universe, a black hole becomes a white hole. As preposterous as this sounds, it is compatible with all the data. When you look at the data from our Big Bang, it is compatible with the idea that these Big Bangs happen all the time. Now, does that prove it? No. It only shows that our particular universe seems to have originated from a peeling process from a parent universe. But it is not proof. Proof, we may have to go to another satellite called LISA, Laser Interferometry Space Antenna, which is going to be a gravity wave detector in outer space, which may give us baby pictures of the instant of creation. The instant of creation, the exact microsecond when the baby universe emerged out of the womb, and the hope is we'll detect evidence of an umbilical cord that connects our baby universe to a parent universe. Sounds crazy? Yeah, but hey, this is what we do for a living. We physicists look at the data, and no matter where the data takes us, that's where we go. And so far, our data takes us in the direction of inflation, which in turn makes possible a multiverse of universes. Okay, let's move on now to the next listener phone call.
Hi, my name is Fred Kushner. I'm in Colorado. I'm not currently listening to, but I do listen to our Colorado Public Broadcasting station. And my question is, if the maximum speed limit for any object or electromagnetic radiation in space-time is the speed of light, why is it that space-time itself can expand faster than the speed of light? That would be wonderful if we could answer that question for me. I'm confused.
Okay, well, Einstein's statement that nothing can go faster than the speed of light is slightly incorrect. A more precise statement would be nothing material can go faster than the speed of light. You see, nothing can go faster than the speed of light. I repeat, nothingness can go faster than the speed of light. In other words, nothing can stretch faster than the speed of light. Now, the Big Bang was when we had this explosion of a tiny area which stretched to give us the universe of today. And that stretching process was not material. It was just emptiness. Empty space can expand faster than the speed of light. But material objects cannot go faster than the speed of light. So, for example, here's an example from my youth. When I was a kid, I used to take a flashlight, and I would sweep across the night sky with the flashlight. The flashlight went from one end of the universe to the other end of the universe, thousands and thousands of light years in the other direction. And I said to myself, now wait a minute. I just violated Einstein's theory of relativity, because the image that sweeps across the sky is going faster than the speed of light. Well, I'm a physicist now, and now I realize that, yes, the image went faster than the speed of light, but material objects, that is photons, particles of light, each particle of light did not go faster than the speed of light. Here's another example. Let's say I have a bomber that drops a whole bunch of bombs in a string, and I'm on the ground and I watch all these bombs hit the ground. Each bomb is moving very slowly as it slowly falls toward the earth. But when I look at the image point of where the bombs hit the ground and then rapidly go bum, 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 bum in a line, I realize that that can go faster than the velocity of the bomb itself. So in other words, the image can go faster than the speed of light because it's not material, but not the bomb itself. Okay, well, unfortunately, we have run out of time in this segment of Science Fantastic. Once again, you can always give us a call at 612-564-8135 and leave that question, make that comment, and perhaps you can get on national radio. Once again, this is Science Fantastic with Professor Michio Kaku. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. Okay, well, let's have the first call.
Hi, this is Tom Myers from Rochester, New York. I saw this on a tweet. What will it take to get the U.S. to use the metric system? Period. Our students are being forced to learn two systems. Their main system, it gives them a handicap when they're using science. This is not a good thing. Thank you.
Yes, I sympathize with you wholeheartedly. When I go traveling around the world, I realize that everybody uses the metric system. Everybody talks in terms of meters and centimeters, except when they come back to the United States. It's back to the old U.S. system. Now, at one point, there was a national campaign years ago to convert to the metric system. However, it never materialized because of, force of habit. It costs money to make a change. And it also is a question of inertia, bureaucratic inertia. You see, politicians don't get points. They don't get reelected by being the champion of the metric system, and people are naturally conservative. Now, in other countries, they have to convert because if you want to engage in commerce, international commerce, then you have to go to the metric system. However, the United States is the 800-pound gorilla. As a consequence, we wanted them to conform to us. Let them convert metric system and our system. Now, it turns out this has practical implications. Years ago, we sent a Mars probe into outer space, and there was a miscalibration because of the conversion from the English system to the metric system, and our space probe was lost as a consequence. So in other words, this has million-dollar consequences. It's not just a question of inconvenience. It's also a question of mistakes are made as a consequence. But Politicians have to get behind it, and unfortunately there's no brownie points that politicians get by pushing something that's unpopular in this country like the metric system. I sympathize with you, but ultimately it's up to the politicians. Sorry about that. Okay, let's move on to the next listener phone call.
Stephen Winter calling from Clinton, Mississippi. Radio station's 103.9 WYAB. My question is concerning global warming. If I'm not mistaken, when I was in high school in the 70s, they were talking about us coming out of a mini ice age or something like that. They were expecting it to get warmer back then. I just wonder what's happened between then and now. Was that information off track, or we got folks wanting to blame everything on CO2 emissions, which I believe one volcano produces a huge amount. Anyway, that's my question. Just curious about that. Thank you.
Okay, well, you ask a question that's very relevant for today. First of all, there are two kinds of atmospheric disturbances. One is long-term and one is short-term. Now, ice ages come and go on a scale of tens of thousands of years. The last ice age ended 10,000 years ago, and that made possible the rise of civilization. Civilizations could not exist when most of North America was covered with a half a mile of ice. And so we were basically nomads going from one small hunting site to another, chasing after the deer and the buffalo, who also migrated. And it was a very hard life. Then 10,000 years ago, the ice melted, making possible civilization. But these are long-term cycles. In another 10,000 years, we will have another ice age. In other words, 10,000 years from now, don't be surprised if America is under a half a mile of ice. Now, the other question is about global warming. Now we're talking about things that change the weather, not on a scale of tens of thousands of years, forecasting another ice age in 10,000 years, but cycles which happen on a scale of decades to centuries, which are usually not natural. Natural cycles usually take thousands to hundreds of thousands of years. But here we're talking about a change that's taking place on a scale of decades. When you look at the last 100 years, for example, you realize that since the Industrial Revolution, temperatures have risen about a degree, that also sea levels have risen at a very measurable rate, caused by the warming of the oceans. Now, the Earth is warming up. You can talk to any farmer. Any farmer will tell you that his or her livelihood depends on knowing when to plant and what the seasons are. And yes, summertime is about a week longer than before. So global warming, just in the sense of warming, is here. Even President George W. Bush years ago said, quote, something is happening, unquote, with the weather that even the average person knows. Now, here's where the debate comes in. The debate comes in as to how much human activity is responsible for global warming. So in other words, even the so-called skeptics will concede now the fact that the Earth is warming up. We can see this with satellite data, oceanic data, but then the question is, who's responsible? Well, we'll talk about that. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a question about global warming. Yes, even the skeptics will say that the Earth is warming. And years ago, I was a skeptic myself. I used to say to myself, come on, now, give me a break. The Earth is so big. It's huge. And humans, we're so tiny. How can we humans influence something as big as the weather? But then you take a look at what's happening with the Earth itself. All the indicators show that the Earth is warming and it's accelerating. We see that all the major glaciers are receding. All the major glaciers are receding on the planet Earth. Parts of Antarctica are beginning to break off. The stability of Antarctica is now being questioned. We see the fact that summer times are about a week longer than normal. And we see that global swings of the weather are commonplace now. 100-year floods, 100-year forest fires, 100-year this, 100-year that. They seem to be happening all the time. And then the big question is, how much of it is due to human activity? Well, scientists use computer programs. Some people don't like them, but what else are you going to do? Use pencil and paper? When you use computer programs to run the videotape, what you find is that with 90% confidence, it is human activity. Now, 90% confidence is not 100%. Scientists are not saying that with 100% accuracy we say that it's human activity, but with 90% confidence they say it's human activity that is causing the Earth to heat up. Okay, well, let's move on now to the next listener phone call.
Hi, Dr. Kaku. This is Ben in Chicago. Are atomic events recorded in space-time similar to the way in which digital data is recorded on storage media? And if so, would it be theoretically possible to read historical events of the past and then recreate them in the present? In other words, you'd be time traveling to the past, not to alter the past, but to gather data of past events and then recreate them in the present, so you could perhaps alter past events in the present. Doing this would avoid any time-traveling paradoxes, and it could be a way to resurrect a dead person by recreating their bodies and memories in the present time in a way that wasn't possible in the past. Thanks.
Well, you actually asked a question that I used to ask myself as a youth a long time ago. Let's say there's a crime. The light emitted from the crime has bounced off the walls, but if you could reassemble all the light, then you could, in principle, recreate the scene of the crime. So I thought to myself, wow, I mean, we have all this knowledge about atomic physics. We have all this knowledge about atoms and photons and electrons. Why can't we collect all this data, not digital data, but atomic data, and then run the videotape backwards to reconstruct the crime? Well, great idea, but in practice it's not practical for several reasons. First of all, when light scatters off a substance, let's say there is a crime and light from the crime hits the walls, light scatters in all these different directions, and to recreate that wavefront would require you to know everything there is about the original wave, everything about the texture of the wall that bounced the light off, and the amount of data would be incredible. And so it's not possible using ordinary techniques to then recreate the wavefront. Sorry about that. However, some people have suggested that even though we can't duplicate the atomic data, the digital data may somehow be reconstructed to create an approximation of reality. This is called digital immortality. One Silicon Valley company is already offering to digitize everything known about you. Your credit card records, your Instagram pictures, everything known about you on the web can be digitized to give you a first approximation to who you are. Now, as time goes by, more and more information will be collected about you to the point that we may be able to reconstruct a reasonable facsimile of who you are. And the Silicon Valley company actually is offering to create a robot. A robot that looks like you, talks like you, has the same mannerisms as you. I've actually seen the robot, and it's not very advanced, so don't get your hopes up. But the question of digital immortality is a possibility. For example, take a look at Winston Churchill. Let's say you digitize everything known about Winston Churchill, so when you go to the library, you talk to him. You talk to a holographic image that reproduces the sound, inflection, historical notes, everything known about Winston Churchill. I mean, I wouldn't mind talking to Einstein. I'd have a great time talking to Einstein, or even a reasonable facsimile of Einstein. And then, maybe decades from now, the Connectome project will be finished. The Connectome project will map the entire brain. Every neuron of the brain can be mapped to recreate a facsimile of your thinking brain, including your memories, your personality. We're talking about a digital version of you that is immortal. Now, is it really immortal? Well, to paraphrase former President Bill Clinton, it all depends on how you define you. If you are a biological being, then no, this is nothing but a digital tape recorder. However, if you is the sum total of all the information that is known about you, your mannerisms, your feelings, your memories, everything known about you, if that is you, then in some sense we have digitized your soul. So your soul is now being reduced to information. Now, is this possible? Certainly possible. Is it economical and practical? That I don't know. But as computer prices continue to drop, some people may want the option of not biological immortality, but digital immortality. Okay, let's move on to the next listener phone call.
Barton Salin, listening on WSRQ in Sarasota, Florida. Since general relativity says that a clock on the sun would run slower than a clock on the Earth because of the greater gravitational force on the sun, if a clock could survive on the sun, doesn't that mean that those time differences between the sun's clock and our clock would accumulate, so that when we look at the sun today, we would not be seeing it as it is today, but rather as it was in the time of the dinosaurs? Now, I realize that today we see the sun as it is today because when there is a flare on the sun, if it's in the right position, we get hit a few hours later by particles from that flare. So we know that we're watching the sun as it is today. Thank you.
Yes, well, you ask a very interesting question. It turns out that the speed of gravity is the speed of light. If the sun were to disappear right now, it would take 8 minutes. 8 minutes for that information to hit the Earth. So even gravity has a finite speed. Now, as you pointed out, time beats at different rates throughout the universe. On the moon, time beats faster. So if I have a clock on the moon and a clock on the Earth, and the two clocks can talk to each other, the clock on the moon beats faster than a clock on the planet Earth. And this is actually measurable. So this is not science fiction. This is science fact. Get used to it. In fact, Einstein once said that he put a clock at every point in the entire universe. He put a clock, all of them beating at a different rate, but he was so poor he couldn't afford a clock of his own. But it's true. Time beats at different rates throughout the universe. So you're saying, can you accumulate this difference in time? The answer is yes, but it is infinitesimal. So if I have an astronaut on the moon and an astronaut on the Earth, a twin, and they eventually meet years later, they will only be a fraction of a second delayed between the two twins. It's a very tiny effect. So don't think that it has any practical applications at all. But you're right. Time beats at different rates. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. That's right. It is open mic on Science Fantastic. Okay, let's move on now to the next listener phone call.
Hey, this is Armand from Queens, New York. I listen to you on YouTube. I was wondering, why do you think Elon Musk thinks that we live in like a simulation? Like, we're a simulation pretty much. We're, made by computers or whatever. I know you believe in the multiverse theory. Well, why do you think Elon Musk believes that we're like a simulation or like a program? Thank you. I love your show. Have a great one.
Excellent question. Well, as I mentioned in my book, The Future of Humanity, we have Silicon Valley billionaires affecting the direction of the space program. And so these people made their money on the Internet. For example, Elon Musk was a PhD candidate in physics, like Wernher von Braun, the famous rocket scientist. Elon Musk also went into the PhD program in physics, but after just 2 weeks at Stanford University, he decided, nope, this is not for me. The money is in Silicon Valley. So people in Silicon Valley think you can digitize everything. But you see, there are limits to what you can digitize. For example, how many atoms are there in your body? I mean, there are 10 to the 23 atoms in a mole. Your body consists of many, many moles. And so the number of atoms in your body could be on the order of 10 to the 26 atoms. That's an enormous number of atoms that you cannot digitize. Take a look at the weather. The smallest object that can simulate the weather is not a supercomputer. Even a supercomputer cannot model the weather and every atom of the weather accurately. The smallest object that can model and reproduce the weather is the weather itself. So we say that these things are not calculable. There are simply so many ways in which atoms can vibrate inside a gas to create the weather that it's simply not practical to build a machine that can duplicate every single atom bouncing around inside the atmosphere. Now, people and reality is much more complicated than the weather. And so that's why even classical physics, Newtonian physics, cannot be modeled using a computer. It cannot be digitized. Now, quantum mechanics makes it worse. Quantum mechanics says that all possible universes are possible, and so you would have to digitize not just one universe, you would have to digitize all possible universes in the world of quantum mechanics. And that's why I say that the movie The Matrix was great, but it's a movie. Get over it. It's a movie. We are not living in a simulation. Welcome back to Science Fantastic with Professor Michio Kaku. Okay, let's move on now to the next listener phone call.
Hello, sir. My name is Dale Phillips. I'm actually not listening to a radio station. I'm looking you up online, and I'm calling from Bahrain, in the Middle East. My question is, I sort of have a two-part question. How close are we to making colonies on other planets, or even the moon, or making colonies elsewhere other than Earth, is what I'm trying to say. Exactly how close we are to doing that. And also, one of my favorite episodes of yours is the episode of Sci-Fi Science where you make the lightsaber. How close are we to making the lightsaber from the time you made that episode to now? So I apologize for the two-part question, but that is my two most favorite interests. Thank you very much. My name is Dale Phillips from Bahrain, and hope to hear from you soon. Thank you.
Well, what a phone call. Yes, I've been to the Middle East, and yes, I'll try to answer your questions. First of all, the colonization of planets is still going to be decades away. Just last December, President Donald Trump issued the Space Policy Directive Number 1. And that Space Policy Directive reversed the policies of Barack Obama. Barack Obama basically ended the U.S. manned space program. He canceled the space shuttle, canceled the replacement for the space shuttle, canceled the moon program, and then also canceled the Mars program. However, Space Directive number 1 says we are going back to the moon, then to Mars, and then beyond, perhaps the asteroid belt. Now, let's be real about this. The timetable, of course, is still speculative. Starting December of 2019, the end of next year, NASA intends to send the SLS booster rocket into outer space, and the capsule will go around the moon, unmanned capsule. Then, around 3 years after that, astronauts will go back to the moon. And then around 2030 to 2035, that's when the first astronauts will go to Mars. And then once we're on Mars, we have to set up a Mars colony. And that'll, of course, take even more time. Perhaps we'll use a lava tube as a makeshift base of operations to protect us against cosmic rays and the harsh atmospheric conditions of Mars. Then we'll create a power plant by putting out solar panels and then begin mining operations. Why that? Because ice is a valuable commodity. Mars has plenty of ice. It's a frozen desert. Ice can be melted and purified to give drinking water, broken apart into oxygen and hydrogen to create rocket fuel for the return mission. So again, first we go to Mars, put our flag on Mars, set up a impromptu base of operations, but then we're talking about long-term operations, basically starting mining to extract water. After that, we're going to set up a agribusiness. In other words, we're going to use genetic engineering to create varieties of algae and crops that can be sustained in the harsh conditions of Mars. The goal is to make it self-sustaining, so it's not going to cost anything at all. For example, it turns out that Mars rock can be melted using microwave radiation. This has actually been done in the laboratory to create duplicate rock of Mars, hit it with ultraviolet radiation, and melt it to create brick. So in other words, it's possible to use the soil of Mars to create brick, which will be used as building materials. It'll be possible to mine the ice to create the first mining operations, and then melting the ice caps using solar satellites to beam the energy down to the poles. Now, we're talking decades. We're not talking anytime soon. But you got to start somewhere. And maybe mining the asteroids could help pay the bill, because the asteroids have plenty of platinum chemicals. Welcome back to Science Fantastic with Professor Michio Kaku. And Science Fantastic, we profile some of the most amazing developments in science and technology. Technology that touches your lives and changes the destiny of nations. Okay, let's move on to the next listener phone call.
Yes, Dr. Kaku, this is Justin from Texas. I listen to KMET. I was just wondering, what do you think the current administration of the United States is going to do about the problems we have with the space station, International Space Station? What do you think? They're talking about, I guess, renting it out. What do you think the best idea would be to use with the International Space Station? Thank you very much.
Well, you ask a very embarrassing question because at the present time, we don't know what to do with the International Space Station. First of all, let me explain what the administration is doing. The Trump administration has issued, at the present time, 3 space directives. Space Policy Directive 1 talked about going back to the moon, then to Mars and beyond. The second directive talked about private enterprise and encouraging the deregulation of outer space. The Space Directive number 3 talked about space junk. So the administration has not yet stated what its policy is toward the space station. Now, it depends on who you talk to. If you talk to a pure scientist, they would say that we get actually very little new science from the space station. So they say that we perhaps don't even need a space station. Other people say, what a waste, $100 billion, and we're just going to let it deorbit and burn up like a meteor. At the present time, the only practical application would be to commercialize it. But we'll see. But unfortunately, we have run out of time in Science Fantastic.